Okay, I'm going to start by looking at black body radiation. So what is this black body radiation? If I take something which is hot, then it gives off heat, which is actually electromagnetic radiation, like light. Now, ignoring the reasons behind it, people know, or we know, that depending on the temperature, you're going to get a combination of infrared, or visible, and ultraviolet light emitted from an object which is really hot. And this is something like what you see. So if you do an experiment and you look at the amount of infrared, that's heat, and visible light, and ultraviolet light given off by a hot object, you can get these graphs. So at around about 5,000 Kelvin, which is approximately the temperature of the surface of the sun, there's a lot of heat, a lot of infrared, all this stuff here, but the bulk of it's given off at white light temperatures in the middle of our visible range, so the sun looks white. As things get cooler, they get redder. So if you put a piece of wire into a Bunsen flame, it's going to come out looking red, not white. If you turn on an old-fashioned light bulb, it looks white because the filament itself is being heated up very, very hot. And in fact, I've got one here. So that is a little piece of tungsten which has been heated up to around about 5,000 Kelvin. Not quite that hot, it's very close to it, and it looks white. Okay, so this is what we call black body radiation. The idea of the black body is that if something is completely black, it's going to either absorb or give off light very, very easily. There's actually a word that we have for that. It's a thing called emissivity, and we're going to look at that in a second when we look at heat radiation. Just as an aside, if I look at this light bulb here, it says it's a warm white, and along here it says it's about 3,000 Kelvin. So this means then that this light bulb is behaving like a light bulb which is heated to about 3,000 Kelvin. So there's a lot more red than there is blue. And you might possibly have seen this on computer screens or in photographic things where they talk about the Kelvin colour, the temperature colour of objects. Okay, so just keeping that in mind, so that's lurking under the next thing we're going to look at, and this is radiation as a way of transferring heat. So if we look at my notes here, you can see that we've got an object, and to make things simple we just tend to take very, very simple shapes. And here's an object, and it's got an area of A. And, well, let's say for example there was this cup of tea here. The area that we'd be interested in would be the surface area around the cup and the area on top, and probably not on the bottom because it's going to be in very close contact with the table. So radiation is going to be coming outwards from here and off the top. Of course there's going to be convection and a few other things involved as well, but we're looking at radiation. So the formula we need for that is the rate of energy coming off is equal to the area times the emissivity. Remember I said that if an object is black, it emits and absorbs heat very well. If an object is white, it doesn't emit it as easily and it doesn't absorb it as easily. You all know that if you are going outside with black clothing on a hot sunny day, it's going to be hotter wearing black clothing than wearing white clothing. And then there's this thing called the Stefan-Boltzmann constant. The Stefan-Boltzmann constant is a number which was derived originally from doing studies on this kind of thing here, and it's a number which allows us to convert temperature, area and distance, temperature and area into an amount of power coming off, the amount of energy coming off. And it's also related to T to the 4 of the surface minus T to the 4 of the environment. Now, T to the 4 is a big number. I mean, if you draw a graph of T to the 4, it goes whiz really quickly. So this means that with small increases in temperature, you actually get big increases in radiant energy. As you can see, the Stefan-Boltzmann constant here is a funny number. It's 5.67 by 10 to the minus 8 watts per square meter per Kelvin to the 4th. Emissivities, as I say, range from small numbers for white, very shiny objects to almost 1 for very black objects. If I get something like this, it looks pretty black. That doesn't have an emissivity of 1. It's sort of about 0.9 or something like that. Because if you looked at it closely, you'd see that it wasn't absolutely perfectly black. Actually, genuinely black objects are things like this. Here's just a little block of metal, and if I make a hole in here, a tiny hole, and I heat it up, this is close to a black body, so that any heat generated in here is coming out that little hole. The reason that that is a black body is that all the energy is coming from here and going straight out. Once it's come out, it can't come back in. You can't get any backwards and forwards effect. The reverse is true. If you shine light into here, if this is very shiny, you're not going to see any light coming back out. Another good example of a black body, actually, if you get a packet of razor blades. I don't have any with me at the moment, but a razor blade, if I look at it on its edge, so here's the blade, it's really sharp, like that. You can go into the hardware store and you can buy these packs of blades for trimming things and cutting things, and they're all just put together in the pack. If you look down the end of that pack at the blades, so this is a classic way of drawing an eye. If we look down there, it looks absolutely black. Rather fun. Try it next time you're in a hardware shop. Okay, so that's radiation. There's some examples here. Work your way through them. They're simple math. Always remember it's T to the 4 of the surface minus T to the 4 of the environment. It's not just the difference between the two. That does not give you the right answers. Now, whoops, these are out of order. The next thing I want to talk about is convection. Convection is one of the three. You've got conduction, radiation and convection. We've looked at conduction, did that in class. We've just looked at radiation. Now look at convection. Again, let's come back to this. I've got a cup of tea here. The outside of this is warm, which the tea's been sitting around for a while. It's fairly cold now. But the air around this is warmed. It rises up and moves off into the room. We call this convection. Now there are two kinds. First one is forced, and the second one is free. So that cup of tea there's got free convection. Forced convection is when you blow on things. So if you want something to cool down quickly, you blow on it to move heat away very quickly. Okay, and let's just have a look at forced first. Forced convection, let's say, as I said, we're blowing on it. Maybe we have a fan blowing on this or something like that, going over a surface. So here's our fan. We're going to use this symbol quite often actually in this course for electric motors driving fans, and so the air is blowing pretty strongly like that. And in that case, we've got a reasonably simple equation. Go over the page here for a moment. We can say that the rate of heat loss is equal to H, this is the convection heat transfer coefficient, times the difference between the surface and the environment. Let's get it there, or it's just that. Okay, so this is a very simple thing. The tricky bit is this. This is actually quite a complex unit. It's composed of a whole bunch of bits and pieces. If we have a look over here, we can see it's composed of, now here we're talking about the fluid. It could be the air, it could be water, it could be something like that. We've got how viscous it is, how well it conducts heat, its density, its specific heat, how fast it's moving, whether it's a gas or a liquid, not a solid, and its temperature. So all of those things have to be considered when you are coming up with this H. H really is specific for a set of conditions. Now, we're not going to go into a lot of detail about these conditions here, but let's have a look at just a couple of little bits to go with it. The first one is H for a very, very simple system. This is air blowing very quickly can't write over a small flat plate. So this is something like this, just blowing over a surface like this, and smooth. So in this case, H is approximately equal to 7.4 times how fast it's going, V, to the 0.8. Now if you draw a graph of something to the 0.8, it sort of goes, it looks almost like a straight line actually, it's got a little bit of a kink in it. So it's fairly close to being the same thing as a linear or a constant function. So in this case here, over a flat plate, it's not too bad. We're going to get a graph which would look something like, well, it's going to be equal to this, which is almost equal to 1 times the temperature distance. So the amount of heat being lost is very, very easy to calculate, but that's only under very special circumstances. Normally you've got to involve a whole bunch of other things. There are two very common numbers, and we're not going to focus on these, but I want to point them out because you may hear about them. There's a thing called the Prandtl number, and there's a thing called the Nusselt number. And combined, these go together to give you a way of describing how convection is going to happen, not at extremely high speed, but at slower speeds. And so if we've got something like this, and we know the Nusselt number and the Prandtl numbers for the outside of this coffee cup or this teacup, then we can calculate how much heat is going to be lost. So just having a look at these, the Prandtl number compares viscous diffusion over thermal diffusion. In other words, how quickly something is being conducted through the fluid versus how quickly the heat is actually being moved away by the molecules moving. And fortunately we can calculate that fairly easily. It's a combination of the specific heat times the viscosity divided by the thermal conductivity of the fluid. And there's another number, a thing called the Nusselt number, which compares how quickly heat is convected away versus how quickly heat is conducted away. It's somewhat similar, but in this case here it's the convective heat transfer coefficient, which we've talked about, times the characteristic length, again by the thermal conductivity. The characteristic length is something that we use in a Reynolds number. Remember Reynolds number? and depending on what we're looking at, we can define this. Now this all gets a little bit complicated when you're trying to do actual examples. I had an example here, but I think we'll just ignore that. The only thing I want to comment on here is that when you've got the Nusselt number, that's equal to the area times the Reynolds number times the Prandtl number. So what I want you to focus on in these is to know that these things exist and that they're used for free conduction, oh sorry, free convection, but that's all you really need to know about those ones there. Okay, so that's the end then of radiation and convection.